6 for Sahil Secant. I'm going to lead you through my code and then show you kind of what the execution looks like. So here we've used a schema where we prefix frame's ID and suffix it in order to generate the path to that frame's image in our folder. So basically, we're going to insert the 3-digit ID for the frame between the prefix and suffix in order to address it. So we put these here for ease of access later. We store the number of rows and columns in our downscaled image in order to also easily access it. And we generate a size for the neighborhood of number of frames that we're going to use to interpolate one frame's image movement. Here I've commented out the actual processing because it just takes a while, and for this demo video it's not really necessary. We can still talk about the code. So here I create an array of structs, each of which has a frame key, and then for each of the 720 images, I zero pad the image's ID, and then fetch that image from the folder, reading it in, converting it to grayscale, resizing it to 45 by 60, and then casting it to double. And then I'm going to store that in the frame key, and that's because that's what the spacetime deriv function takes. So now we've got a solid list of frames, and that's why I can comment it out, because we never actually changed this f array later, so I can just use what's in my workspace. Okay, so here we create an array to hold the average velocity that's going to be the size of the number of 7 block sections that exist in the 720 frames. So we're going to loop through each of those 7 block sections sequentially, where I is going to index the first frame in that block, and I plus 3 is actually going to index the frame that we're interpolating motion for in that block, which is the middle frame. Here we show the actual unscaled frame image on the left, because I just find it better for visualization. But we're going to be doing all of our operations on a scaled version in order to reduce computation time. So here we calculate the derivatives for this neighborhood-sized block of frames, and these are going to be stored in fx, fy, ft. And then we generate various product combinations of fx, fy, and ft, which is just going to make it easier when we're indexing into them later to create our M array. We create an array to hold all the velocities for each point in our image, and then we also create another array that's going to hold the x and y coordinates of points as well as the velocities for points that have non-zero velocities. And that's just going to allow us to use Quiver quite easily later. So we loop through all of the pixels, leaving a 4-pixel border as designed. And here we're going to generate the M matrix. So the M matrix has 4 entries. Top left is going to be, and each entry is basically a sum over the neighborhood. The neighborhood is going to be defined as 3 pixels to the left, 3 pixels to the right, 3 pixels above, and 3 pixels below our current pixel that we're indexing. And that's going to create a 7 by 7 pixel neighborhood. And so we're going to sum over that neighborhood for each of these arrays that we generated to create M. And that's going to create M as we wished it. And now we're going to check if our linear system is unstable. If it's unstable, we're basically going to want to skip even calculating what a motion is for this, because it's going to be very inaccurate. Or if the motion is very low, there's no particular reason to do so. So we're going to go ahead and do that. And once we've checked that, we can basically be sure that we're avoiding problems of rank deficiency in our M matrix. So we can actually invert it nice and easy and solve for the current velocity based on this vector B. And we're allowed to do this, as I said, because we've already checked for rank deficiency. So here we store V, our velocity, and we store it into the quiver data for this pixel, and we move on to the next few pixels. Once we've done the entire frame, we've generated basically an array QD that holds the x and y coordinates as well as the velocities at every point that has non-zero velocity in this frame at this time. And we're going to rescale this whole thing, because we're going to be displaying this over the unscaled image, so we have to rescale it up after our computations were done on a smaller version. So we rescale all of QD, which also scales the motions, place a quiver plot, making sure to invert the y velocity because it's going to be pointing in the wrong direction because of the way MATLAB orients images. And then we're going to take the mean of the non-zero entries of y velocities, which should be all of them basically, and we're going to store that in the average v for this frame, excuse me. Once we've done that, we plot all of the average velocities we found so far over time in order to hopefully discover some sort of sinusoidal motion. So let's actually look at what this looks like in totality. So here we're running it, and as you can see, as the plant moves upward slowly, we have a properly scaled quiver plot that shows that it's detecting a lot of upward motion here. And this is also evidenced by, on the right side, our average velocity being above 0. Now we dip below as the plant goes down. So what we're trying to see is the periodicity, and we see a very nice, clean sine wave. And that sine wave is going to be what we're analyzing to see what the periodicity of this plant's cycle is. So we don't actually need to analyze the whole thing because this is very clean, but I'll keep running this and let you see it do its thing. But we can actually take a look at the periodicity, the period of this motion. So if you can see here, here's where we start, and then we finish here at the same place. So the time it took us to get from here to here should be the basic period of the motion of this. And if we trace this downwards, we can actually see that it comes out to around 1500 minutes in. And actually, a day is 1440 minutes, which means this cycle takes place and resets every day, which is exactly what we'd expect from class. So I don't need to show you any more of it, and I think that should be good, and that's all.